Okay, so this is WFA number 10. I don't have my pencil, my Apple Pencil, so I'm just gonna use my finger. So if it's messy, I'm sorry, but let's go ahead and start and see what the questions are. Probably torque and stuff. So for a wheel spinning with a constant angular acceleration on an axis through its center, the ratio between the speed of a point on the rim to the speed of a point halfway between the center and the rim is. So this there you go. That's the wheel spinning through with some angular acceleration. And I'm pretty sure the angular acceleration doesn't really have an effect on the speed, as in it'll clearly speed up, but if you were to look at like the speed at a certain instant, right, we don't really need to worry about the acceleration in that case because we're just looking at a particular instant, right? It'll be having some angular speed omega, and we know that omega is equal to v over r. This is actually one of the bridge equations, right? This comes from like theta equals distance over r. And so you just take the time derivative on both sides and you get this formula. Constant omega for both points, but if you have... Is this the right equation? Yeah, I guess it's better to have it in the form v equals omega times r, because if you have double the radius, you'll be moving twice as fast. For spin... same scenario, I believe. The ratio of the tangential acceleration of a point on the rim to the tangential acceleration of a point halfway between the rim is, and so I'm gonna assume it's the same scenario, because if it's not accelerating, then it's just going to be a 1-to-1 ratio, right? 0 to 0. But assuming it does have that constant angular acceleration, you're going to have, it's the same bridge equation really. A is going to equal alpha times r. If you have double the radius, you will have double the angular acceleration. For same scenario, the ratio of the radial acceleration of a point to the rim to the radial acceleration of a point halfway between the center and the rim. So this one's kind of interesting because you could use the v squared over r is equal to a. So a point, it just becomes a little bit crazy because you say, okay, if you're twice as far, you have this, you have double the you have double the radius, but you would also have double the speed. You just square that, you have 4 times, so it should be a 2 ratio. And remember, wait, no. Does that make sense? You have twice the radius. Because if you use a bridge equation, A equals omega squared r, this is actually a bridge equation you could, or not a bridge equation, this is just a centripetal acceleration. If you replace in omega as omega times r, you would get omega squared r squared. One of them would drop. So, oh yeah, you have twice the radius. Okay, yeah, that actually checks out. So it should be 2 times as much. A wheel starts from rest and spins at constant angular acceleration. As the time goes on, the acceleration vector for a point on the rim, so it's going to increase. So this is kind of interesting because if you have a point on the wheel, there's going to be an A there's going to be an A in this direction, right? That's going to cause it to accelerate, and there's going to be an A radial. That's what I should say. A tangential, and then an A perpendicular. The A tangential won't change, but as it speeds up, using this equation, we know, hey, oh, but wait, you have this omega squared. Oh, but omega speeds up. Yeah. So the centripetal acceleration will grow larger. So it'll increase in magnitude, but become more radial. So the center of mass is labeled as shown. This is interesting. Okay, so look at the diagram. Center of mass is over there. Our Sorry, I just got a random text. Center of mass is not aligned. If it were in the middle, the wheels will exert a force that is going to be 1/2 mg, right? Because if you think about the FBD, this is in the middle, so this will be 1/2 the weight. This would be 1/2 the weight. But because it's a little bit closer to this side, right? It's about 1/3 of the way from here. You can imagine, hey, this force will be a little bit larger and this force will be a little bit smaller than 1/2. Because if you draw your axis of rotation right there, now mg is going to be creating a larger torque about that axis of rotation. So to counteract that, your back wheels need to exert a larger force in order to produce a larger torque so that the torques are balanced. So in other words, torque wheel minus torque weight is going to equal 0. Torque weight is going to be like force, torque of the wheels is going to be the force that we're solving for, times, we'll call it the distance d, right? It's like the distance between the wheels is a distance d. Yep, so there we go. We don't need to worry about sine theta or cosine theta because the force is completely perpendicular to the lever arm. Or I guess, I think that's a fair explanation. So then we're going to have weight times, if this is d over 3, then this distance is 2d over 3. So we're going to have 2d over 3 is going to equal 0. So I'm going to have F. I can drop the d and I would get equal to 2/3 the weight. Or mg, which is the same thing. Pulley is initially rotating in the positive direction and slowly comes to a stop. So these are all theta versus omega, theta versus time. The slope of theta versus time is the angular acceleration. So I'm saying, hey, or angular velocity, saying, hey, when is the slope flatlining to 0? Graph C is like, hey, this thing is just at rest completely. Graph B is a constant angular velocity, which is not going to be slowing down. Graph A is really the same as graph E, but in the opposite direction. It's speeding up. This one's speeding up positively. This one's speeding up negatively. In the negative direction, I should say. That's a more apt description. So graph D is going to be our solution. Let's see how I did. And I hope I didn't mess up. Okay, beautiful.